Good afternoon, everybody. Since we had a little delay, apologies about that, and thank you for your patience. I will keep my introduction short so that we can enjoy Dr. Okolo's talk. Dr. Wendy A. Okolo is an aerospace engineering researcher in the Intelligent Systems Division at NASA Ames Research Center. Her focus is in the area of systems health monitoring and control systems design with applications to air and space components, vehicles, and systems. To that effect, she manages a multi-million-dollar sub-project on a system-wide safety project, leading a team to develop the monitoring, predictive, and mitigation capabilities that will enable the safe operations of unmanned aerial vehicles. At 26 years old, Wendy became the first Black woman to obtain a PhD in aerospace engineering from the University of Texas at Arlington. Her graduate studies were recognized and funded by the U.S. Department of Defense through the National Defense Science and Engineering Graduate Fellowship, Zonta International through the Amelia Earhart Fellowship, the American Institute for Aeronautics and Astronautics, and the Texas Space Grant Consortium. Other research awards include a resolution of commendation from the Tarrant County Court of Texas and an award for excellence in research by the Women of Color in STEM. At NASA, she has received a number of awards, including a NASA Ames Honor Award, an Ames Innovation Fair win, a NASA Space Technology Early Career Initiative Award. Dr. Okolo is also the recipient of the 2019 NASA Ames Early Career Researcher Award, the 2019 UT Arlington Distinguished Recent Graduate Award, the 2019 Women in Aerospace Award for Initiative, Inspiration, and Impact, and the 2019 Black Engineer of the Year Award for Most Promising Engineer in U.S. Government. Please help me welcome Dr. Wendy Okolo.
Okay, well, thank you all for coming, and I'm really excited to be here. Thank you for the invitation, Deb. Like Deb said, I wear quite a few hats at Ames, and today I'm going to be talking about one of those hats. And please feel free to ask me questions, might be a little interactive, a little too technical. There are no dumb questions, especially for the young people in the audience or the non-engineering, non-technical people. I want to hear the questions, okay? So today I'll be talking to you about one of the really, really cool things I get to work on, which is this project called Pterodactyl. Pterodactyl, how do you come up with a name like that, right? I work for the government, so we like our acronyms, and we're looking for this cool name to make something fly, and came up with Pterodactyl and tried to find like an acronym of what it would actually stand for, like precision targeting, entry. Well, it didn't quite work out. I don't know what we ended up doing, but it's Pterodactyl now, and it's a really, really large project. And you know, just an overview. It's a big project. It's a large team of people located at NASA Ames Research Center, at Johnson Space Center. Who knows where Johnson Space Center is? You're not allowed, Danny. You work at NASA. How are you even here? This girl works at NASA with me. Who knows where Johnson Space Center is? Yes. In Houston, we have a problem. So we're at Ames, we're at JSC, we have partners at the Applied Physics Lab, Johns Hopkins Applied Physics Lab, we have partners at UC Davis. So it's an early career, project that we put a proposal together. About 5 of us put this proposal a couple of years ago, and NASA headquarters, the Space Technology Mission Directorate, gave us $2.5 million to go crazy, and we did. So the names that are bolded here are the controls team, that consists of myself, Benjamin Margolis, who is a controls engineer, pathway student now, full-time NASA employee, and Jeffrey Barton, who is at APL. So we are the controls team, and I lead the controls team of these people. So there are, all these different facets to the project, and I'm the controls lead on that. And so what is Pterodactyl, and what is this work that I'm going to be talking to you about today? So the motivation behind this work is really that precision targeting, right? So if you have an entry vehicle or a spacecraft set to land in a certain area, the closer you are to your target, the more improved your precision targeting is, the easier, the more cost affordable it is, operational recovery costs, and timely sample renewal. So you don't have like this large envelope right, that you're going to get your spacecraft back from. You can kind of do better with precision targeting, and that's really the big picture. How can we improve precision targeting? This is driving, a new class of vehicles that will enable small and large mass missions to other planets, lunar sample return for us to go to Mars in support of the different programs that NASA is embarking on. One of the big ones is, what's the big thing we keep hearing NASA talk about these days? Mars. What's the program called though? What is it? It's not Orion. Orion is a big one, but what is it? What is Orion going to support? What's the big thing? I'm going to give you a hint. Apollo. Any takers? Apollo had a sister, like Greek mythology. Artemis. She gets NASA gear. The Artemis program. So Apollo had a sister. We went to the moon. The 50th anniversary of it was last year. Went to the moon and did all this cool stuff and everything. And we want to go back. To the moon and land the first female, the first woman on the moon. So we're calling it Artemis. We're trying to go back and actually do some really sustainable, cool stuff there. And so, if you're on the moon and you want to send a sample back or you want to do something cool and you don't really need a large spacecraft or something on the order of the Apollo capsules, there's this new class of vehicles that can achieve this, and they're called Deployable Entry Vehicles. So these small and large missions are kind of driving these, and a deployable entry vehicle doesn't really have that rigid body when you consider the Apollo capsule is something that is stowed, and then during entry, it deploys. So when you have something that's small that can then deploy, it means you can, reduce the volume constraints you have. So the one we're actually working with works like an umbrella. It's stowed like an umbrella, and then it deploys during entry. And so the challenge with these kind of vehicles is because they don't have that rigid form, right? Imagine like a bowl with a lid, like Tupperware. It has a rigid form, so you can put things on the back of it, right? You can stick things there. Well, these don't have a rigid form, and traditionally, entry vehicles were controlled by putting thrusters on the backs of these vehicles, right? That's how we've controlled entry vehicles for as long as remember. You can put reaction control systems that can fire in pairs on the backshell, as we see on the left hand of that plot. So you can put RCS is a short form of reaction control system. So you can put RCS on the back of these vehicles and control these vehicles for heritage entry spacecraft. But when you don't have a backshell for a deployable entry vehicle, what can you do? And that is what this project is really trying to solve. Looking at control systems, how you can control a deployable entry vehicle, what kind of control systems can feasibly be integrated on something that doesn't have a rigid shell that stows and then boom, deploys during entry. So DVs have no back shell. You have your payload and other subsystems in the back, and that's the forebody. So how do you control this thing? And so again, the research question that we're trying to answer in the past couple of years is what control system can be integrated into the DV and enable steering to a target location precisely. Remember what I said, we want to improve precision landing. And so here's the baseline mission that we're looking at. On the left side, you see the descent activation system. On the right side, you see where active guidance starts. So when you think about entry, there are multiple phases. There's the entry phase, there's descent phase, and then there's the landing phase. We're concerned with the entry phase of the vehicle moving through the atmosphere. So we're looking at a lunar return mission, kind of like a stress case for loads, which is why we chose that mission, focused primarily on the entry phase, and that's the entry interface that we're looking at, altitude and velocity. We're not concerned with descent activation or whatever parachute or landing system actually gets it into the ground. We're just saying, if you look at that footprint, that space where you're supposed to be targeting, how well are you doing with that? And so this is the baseline vehicle, the Pterodactyl baseline vehicle that we're working with. We can call it a PBV. And it's an asymmetric vehicle. It's asymmetric. Who can tell me, looking at this vehicle, why it's asymmetric? Just looking at the picture on the left-hand side. Let me check it. Yeah. offset the CG. But why would we consider this vehicle asymmetric? Can I point with this? Is there a laser pointer? Top button. Oh, wonderful. So this vehicle right here, why would we consider, what is symmetry in the first place? What is symmetry? When something's symmetric, what does that mean? Yes, so one half is similar to the other half, right? So it's symmetric. We hopefully are mostly symmetric, right? Right? I hope. So one half is similar to the other half, but that half doesn't have to be left-right. It can be up-down. So why is this vehicle not symmetric? There's what? This side is shy. Who said it? Yeah, the leading edge is shorter than the trailing edge, so there's more on the bottom here. Maybe I should kind of look on this side too. There's more on the bottom here than on the top. So if it was a perfect circle, it wouldn't be asymmetric. And this is important. I'm pointing this out for a reason. This vehicle is asymmetric. The vehicle, our baseline vehicle, this vehicle exists. We took that and said, okay, how can we make this deployable entry vehicle fly and do some tweaks and mods to it? But it is not a symmetric vehicle. So that's going to be interesting, right? It's not a perfect circle. There's more on the bottom than on the top. So it's not symmetric. So this is the baseline vehicle that we're working with. And its importance, the importance of this asymmetry will come in subsequent slides. The diameter is 1+ meter, mass, LVD and alpha, don't worry about those. So leading the controls team, what do I care about, right? Remember I said this team is a large group of people at JSC, Ames, APL, UC Davis, mentors, different teams. As a controls engineer, my background is controls, what I got a PhD in. What do I care about? What is controls, right? When you think about aerospace, there are a number of different disciplines. There are people that care about structures. That's like the body of it, the material, right? You sitting on that chair now, can that chair withstand the weight that you're putting on it? That's what a structures person probably cares about. There are people that care about propulsions. What is propulsions? The engines, right? And how much thrust you can generate, what kind of thrust you can generate. The people that are aerodynamicists, right? Aerodynamicists in various forms. It's not even just aerospace, right? Mechanical engineers, aerodynamicists that care about cars and the way the cars are shaped, the streamlined shape of the cars that can help reduce drag. So I'm controls. There's a field of guidance, navigation, and controls. Guidance is where do you want to go? Navigation is where are you now? Controls is how do you get there? Right, so it should probably be NGC, not GNC, but everyone calls it GNC. So as a controls engineer, I care about one, taking the aerodynamic data that basically describes this vehicle, taking the mass and inertia properties of this vehicle, and then understanding it, right? First, you want to have an intuitive understanding of this vehicle, what it can do, what are its limits. Create a representation of vehicle, and I'm going to show some slides about that, and that's just the math. Right, looking at that vehicle in the previous slide, what does this mean? What can the math about this vehicle tell me about, what I can do with it? Then utilize this information to command the vehicle to follow guidance trajectories. Guidance is where do you want to go, right? So guidance tells me this is where I want to go, and then I use my controls information to move the vehicle there. And it can be position, X, Y, Z, it can be velocity, it really can be anything, any states. Like I want to command the states to move from where they are now to a desired state. That's what controls is. So now you just got a crash course on controls, aerospace engineering controls. How many people here are going to be controls engineers? Ha! So and then compare the different control systems that we're going to look at and then down. So like this is more for the group as a whole. And so here are the control systems that we look at. The first one was reaction control systems, as I had shown for the heritage entry vehicles. What they typically have is like the thrusters and the backshells that fire, and they can kind of fire in pairs to maybe rotate the vehicle one way or the other. The second is flap control systems. Who that is not an aerospace engineer knows what a flap is in terms of aero? Okay, it's what? It's like a wing. It's like a wing. Have you ever been on a plane and looked out the windows, and you see the wings, right? You can see the wings, but then you see these flaps on the kind of like the backside going up and down, and you wonder, what is that? Right? There are people that wonder. I had a friend ask me, like, why don't they control those things? I'm like, those things are used to control the plane. It's mind-blowing, right? So they're aerodynamic control surfaces, and when they move one way or another, the plane does something. So sometimes you'll see the ones go up on the right side, the others on the left side, and your plane will roll, like conduct some sort of maneuver. So those are actually control surfaces. So instead of your engines firing, you can put flaps and then deflect them one way or another to make your vehicle roll, pitch, or yaw. And then moving mass control systems. Basically, this is just moving a CG around. Someone had said something about a CG offset, right? So imagine this, this is just, imagine if I didn't have this like solid footing on the ground and I had my hands out like this, and then all of a sudden you place the weight here. What would I likely do if you put something really, really heavy on this end? What would happen? Exactly. It would roll, it would like rotate this way with this axis of rotation. So if you move mass from one side of a body to another, you're going to cause it to rotate. So you could maybe try to look at that for controlling the vehicle, rotating and following, guidance commands. So reaction control systems, RCS, flap control systems, FCS, and moving mass control systems, MMCS. So I might use these interchangeably. I will not quiz you. So if you don't remember, that's fine. So these are the control systems that we look at. What's the flap design like? So if you remember the body, the Pterodactyl baseline vehicle body earlier, we put flaps on them, as you see here. 2 on the top, 2 on the bottom, 2 on the right and left. 8 flaps to increase control authority and reduce multi-axis coupling, because this vehicle is not symmetric. When you roll it or you do something or you yaw it, you get some coupling in ways that you wouldn't really expect, but it's not symmetric. If it was a symmetric vehicle, you wouldn't have as much of that. And so to reduce any, we already have a question.
Why was it designed asymmetrically? Why wasn't it designed asymmetrically?
So there is a symmetric version of the vehicle, but this is going to get a little interesting. Because it's asymmetric like that, the lift to drag is higher, right? So the L over D, anyone? Yeah, the lift to drag ratio is higher. And when you have a high L over D, that vehicle was actually designed to follow bank angle command. So when you have a higher L over D, you can do more in terms of guidance. So they added that more, the longer gore and the ribs on the bottom. So we took that vehicle, took the most complicated thing and decided, how do we control this vehicle? Right? We could have gone simpler, but I don't know. They gave us $2.5 million. We're like, let's go crazy. But yeah, so it was to improve the L over D, and you can do more in terms of bank angle control. Yes?
Since the vehicle is asymmetrical, does that also mean that the flaps are not all even, that some of them had to be maybe a little longer, some of them had to be in different shape because of that?
Yeah, so they happen to be, but it's not because of that. It was packaging and stowing requirements that made like the ones on the bottom a little shorter than the ones on the top, but that's a very, very great question. The asymmetry will manifest in different ways as you go through the design process. But from a flap design standpoint, the asymmetry, or from a controls standpoint, I didn't really care about the asymmetry, is how much control authority could I generate? The flaps had to be sized big enough that when I would deflect them, they were able to do enough of what I wanted the vehicle to do, to fight any coupling or deal with anything like that. That's really what I cared about.
Because what I'm thinking of is the flaps on the side that is, say, lighter,
Yeah.
would have to be bigger than the ones on the heavier side, correct?
Possibly if you're trying to generate equal and opposite commands, but you might not, right? There's some, yeah, you may not, like depending on, so there's some L over D. What if you want to perpetually remain like in this orientation, and then you might not need to pitch up as much as you need to pitch down. So it kind of depends on what the goals are, and that kind of tells you why there's this interplay between guidance, where you're trying to go, controls, how you get there, navigation, where you are. Yeah, these are great questions. So this is what the flap design is. Just some more information about the vehicle with flaps integrated, and then the flaps can go from -4 to 5 behind to 20 degrees into the flow. These are just aero and pathogen and aerothermal constraints, right? We're talking entry. So if you go too far into the flow, then you start to have heating, you start to have heating restrictions and shock waves and things induced in the flow. So this was a bound placed by us for the vehicle based on pathogen and aerothermal constraints. The moving masses, similar to the flaps, we put 8 on there, actuation similar to the flaps, and then the mass size limited by the stowed state. First cut starting. The same with the RCS, it was just that we had APL do the sizing study for the reaction control systems, and they recommended locating thrusters at a certain reaction radius and recommended the kinds of impulse requirements as well that we would need. So we have 4 rib thrusters mounted that can generate 1 Newton nominal thrust. Don't worry about that. But basically, this is just an overview of the flap control systems, the reaction control systems, and the moving mass control systems. So I talked about bank angle commands for guidance. So heritage systems would typically do bank angle where basically they're changing one of the angles. The bank is, one of the important aerodynamic, parameters. They're changing the angles to kind of modulate lift. So you have your velocity vector, and then if you change that angle here, you can change the direction in which your vehicle is facing or where it's going. But then you can also do another thing where you change, instead of just the one angle that's coupled and moving your lift vector and all of that, you can change your angle of attack, which is basically how you're pitched up, and you can change your side slip. So if you want to go up and kind of increase your downrange, you can change your angle of attack. If you want to steer left, you can change your side slip. So just remember this, angle of attack is for up, down, kind of, and side slip is kind of like left, right. So this is an alternative to what heritage vehicles typically do for guidance. So you can do bank or you can do alpha beta, which is angle of attack and side slip. So I'll typically say bank or alpha beta. And of the vehicle, so we started out with this baseline vehicle that already existed. We're calling it the Pterodactyl baseline vehicles because we had to make some modifications to it. That baseline vehicle is based off a lifting nano-adept vehicle. So NASA had about 4 deployable entry vehicles, like 4 unconventional vehicles under consideration for these Mars missions. It was an inflatable one, Hyatt. So you know how this kind of deploys with like an umbrella with like the rigid struts and stuff. Then there was Hyatt that would deploy like a floater, kind of like pneumatically. So there's Hyatt, there's the Adept vehicle, there was the MRV, and then there's one more that I'm forgetting. What was it? Drawing a blank here. So we took that base vehicle and then went through like the packaging, like the CAD models, and basically came up with something that resulted where we could add the flaps, RCS, and MCS. But we started with the baseline vehicle because we were concerned, what we're trying to do was not design a deployable entry vehicle, but design a system that could control and integrate a control system on an entry vehicle. So we had a starting vehicle to work with, which is an interesting question because then we're basically saying, give me a deployable entry vehicle or give me any entry vehicle at all, and I can control it in ways that are unconventional. Yeah. Okay, so flaps, moving masses and RCS, the capabilities to do alpha beta control or coupled downrange control. For the flaps, it's our flap deflection angle into or out of the flow for each of those 8 flaps. For our moving masses, it's how far are you moving each mass along the ribs. So you imagine this umbrella and then you have masses on each rib and then you're moving them in and out. How far do you move to control? And then for the reaction thrusters, you're just firing on or are you firing off? That's it. So these are the control outputs. For one, you have deflection angles. For the other, how far are you moving the masses? For the third one, are you firing on or are you firing off? And so I take, yes?
I assume you have software that's going to calculate your thrust and the duration of fire.
Mm-hmm.
Where is that located? Is that software on the vehicle or is it on some other?
I will get to that. Okay. So, but that really is the next, that's the crux of this, right? So you have all of this information, then how do you simulate it? So entry systems are pretty simple in that they don't require a significant amount of computation on board. It's typically done on board, but you have all these pieces from the different places. You have aerothermal, you have the aerodynamics, you have the controls, guidance, all of that working together. A lot of this is done offline, which is what I'm going to show you, and then it's it's pretty simple, relatively easy computation that can be done on board. Okay, so we have all of that information, and then we want to develop a simulation model, design, control. Now that we have all these different pieces, right? Where's the math? Who's excited about the math? Yes, okay. So this is Aero 101 that I got from the NASA website. I was putting these slides together. I was like, okay, well, I don't really know my target audience, and let me just, give you some, you're gonna enjoy this. So, but this is publicly available, like information you can teach kids, literally, like forces and moments on a plane. And you can teach yourself too. Any of those, I didn't like math growing up, this stuff is easy. So imagine an airplane that has a vertical force going up, that force is called lift, and a downward force called weight. When your lift equals weight, you are in something you can consider like an equilibrium. You're trim, means, you're not accelerating up or down, you're here, right? Because you're equal and opposite. Thrust and drag work the same way, but in different axes. Thrust moves you forward, drag slows you down. Drag is not always a bad thing. When you're landing, you want drag, right? You don't want to poof, accelerate, off the runway. So drag, it's not a bad thing. So these are the 4 primary forces on an airplane. There's side, but we can ignore those for now. Remember I talked about those flaps? So next time you're in a plane and you can see through the window and look on the wings, you're going to be mesmerized by the way these things move up and down on the edges of the wings. So when your lift is greater than weight, what happens with the plane? It goes up. When it's less, goes down. When drag is greater than thrust, the plane slows. When thrust is greater than drag, your plane accelerates. F equals ma, right? Force is mass times acceleration. Okay, you're with me. Then there's more. I showed forces, right, in different directions. There's more. There's roll, pitch, and yaw. These are called moments, or what's another word for moments that the mechanical folks typically like? So I'm an aero girl. I call them moments, but mechanical people call them torques. Right? So people are more familiar with torques. They've heard of a torque. A torque is a force moving through a distance, right? So again, put weight here, that's a force. Boom, that's the distance, right? So force moving through a distance, that's a torque or that's a moment. Depending on what direction that moment is happening, right, is what determines if it's a roll, if it's a pitch, or if it's a yaw. But they're all torques, they're all moments. A roll is a rotation about kind of like the nose coming out. So this is a really great way to explain it. This, if your plane is like this is a roll when it's doing this. Can everyone see that? This is a pitch. And then this is a yaw. Right, exactly. So, and then your force is basically just this or that, or, but depending on what axis you're rolling around, roll, pitch, and yaw. So I put this here to kind of show, before I get to the equations, that I'm going to show some equations, but I don't want you to get hung up on the equations. There's just a few key things that I want you to, to take from those equations. Don't ask me about these equations. It's going to take 3 hours to get to all of this. But I just want to show you, so you have this vehicle, that can be represented with a set of equations of motion. These equations of motion are typically nonlinear, right? But they are dependent on the forces I just showed you, your drag, lift, and side forces, and then the moments I just showed you, right? That's what's key. These things go into the equation. So when you talk about representing a vehicle, you have to understand how that vehicle depends. What are all these things that go into the representation of that vehicle? So it falls out of the math. So you need those aerodynamic forces and moments, right? These equations are pretty standard, right, for an entry vehicle. What changes is what are those aero forces and moments that are going in? What is the inertia? What is the mass distribution? Inertia is how is mass distributed, across a body, right, through a body. So what are those parameters that change? That's what really changes, because all these things go in here. And a vehicle will change from another vehicle depending on what you fill these equations with. And so these forces that I talked about, side force, lift force, drag force, roll pitch, and yaw moment, they have coefficients. So an aerodynamicist will give me these coefficients. And for an aircraft, right, because we don't go that fast through the atmosphere. I mean, you might think we go pretty fast, but we don't. It still takes us 6 hours to get to DC. 6 hours. Deb, 6 hours. Why am I in a plane for 6 hours when the technology exists that will get me there in an hour and a half? It's just a little loud. But people don't like that it's loud. They complain. This is a true story. They actually complain. That's why we don't do it. And they complain, and Congress passed a law that says you cannot fly supersonic over the continental United States. But it exists. So next time you're stuck in a plane for 6 hours, just know you're stuck there because people complained that it is too loud and their dogs and cats are going crazy. True story. It's in the papers. But so airplanes don't go really fast. So your aerodynamic coefficients don't depend. They really just depend on like angle of attack and pitch and the deflections and things like that. But when you get into space, right, spacecraft entry, there's a lot that's changing. Your Mach number. Who knows what Mach is? Who knows what Mach is? Okay. Speed, it's very, very heavily dependent on speed, but it is in relation to the speed of sound. So when you're a Mach 1, flying at the speed of sound. When you're greater than Mach 1, you're supersonic. When you're way greater, you're hypersonic. Then you get to transonic. When you're below Mach 1, subsonic, low subsonic regions. So depending on how fast you're going, right, these things kind of affect the aerodynamics of the vehicle. So when you get into entry and spacecraft, it gets a little more tricky. Dynamic pressure, Q bar, half rho v square, depending on velocity as well. Then your alpha, beta, your angle of attack and side slip. I'm going to say alpha, beta a lot. Just know alpha is angle of attack, beta is side slip. And then your aerodynamic data also depends on these aerodynamic control surfaces. Remember, so if you're deflected all the way into the flow, the aerodynamics that the vehicle experiences is a little different than if you're not deflected at all. So all of these go into those equations. That's all you care about with those equations. So you need your aero forces and moments to characterize the vehicle and design the controller. And your aerodynamic forces and moments are dependent on these coefficients, where these coefficients have dependencies on the baseline vehicle, and they also have dependencies on the flaps when you're looking at the flap configuration. So if you're not looking at the flap configuration, these terms right here on the right side just go to 0. So for the flaps, because they're aero surfaces, they also contribute as well. So you take those nonlinear equations, you want to take them from nonlinear to linear, so you linearize through a process that we will not go through today, and you're trying to get this gain matrix K. Remember I said controls is taking you from where you are to where you want to go. And so X, consider X as where you are, your state's now where you are, X desired is where you want to go. And there's this magical K gain matrix that when you figure it out, it'll take you from X to X desired. And so you basically plug that U back in here, you get the plant dynamics, this closed loop, and you solve for K such that 1, your system is stabilized, 2, your system goes from X to X desired while balancing objectives. What are the objectives? How fast you want to get to X desired. You're here, you want to get there. How quickly do you want to get there? You want to do a leap? Do you want to walk slowly? These are all the things that you, as the controls engineer, you want to kind of figure out how fast do I want to get there? And then how much energy am I going to use? Like how much control effort am I going to use? What's worth it to me? Is it worth it for me to jump and be out of breath and then come back here? Maybe, maybe not if I'm going to jump and then just go home. But if I have to come back here and speak, I'm probably just going to walk. So you're balancing all these objectives. That's what controls it. It is so cool, right? So it's like how fast you want to get there. How quickly do you want your states to get there? How much control effort do you want to use? These are all the things that kind of go into that. And so you work through all of that so that you can get your control design. And we did this linearization split based on something that I did in my thesis for my PhD, such that each time we get an update from the aerodynamics team, remember I said this project is, multiple people working together, so aerodynamicist gives me info, and I'm like, okay, this is what we can do with this vehicle. and then I pass that onto the guidance, and then they run the trajectory knowing the limits of control, and is it good enough, and then we work back. It's a very, very iterative process. And so each time the aerodynamicist gives me info, I can work through that entire process, or I can split it such that it's not everything that's changing at every time. So this is really, really cool. And I'm going to show some references if you have questions. Like, this is all like been published since my PhD days of a few years ago. So it's public information, and you're not basically linearizing each time. So if you think about that entry phase that I showed you from entry, during entry, the vehicle goes through different Mach numbers and different dynamic pressures, M and Q, Mach number and dynamic pressure. And you can, like I said, linearize your equations of motion and then evaluate at different points. So your vehicle, take this, your vehicle is represented by a set of nonlinear equations, but you want to design a linear controller for them, because linear is good. Like linear is good. Linear is easy, right? So if you linearize, so you kind of linearize in a region and say, this is valid in this region. And then you can test it in another region and see how well you do, right? And most times for entry vehicles, because things aren't as crazy, you're usually fine. If you linearize here, you can usually fly here with the same, assumptions you made, and things kind of work out. So you can pick a point and linearize. We did 2, but we ended up just using 1 because 1 worked fine. And then can utilize that controls design for the 3 RCS, FCS, and MMCS control systems. Who remembers what MMCS is? Moving mass control systems. Yes, you're with me. Okay, so you can utilize the control design for all 3 configurations. But first, we want to understand in what regions can we control this vehicle? What are the limits of controlling this vehicle? This is going to get into that asymmetry versus symmetry conversation, and where we're limited, and what happens when you try to control, and what are the things that happen. So what are the limits of controlling this vehicle before you even start the process? So ignoring these curves, because it's going to take a while to explain, what I just want to note is that when you induce a yaw moment on this vehicle, when you cause this vehicle to do this, it also happens to want to do this. But this is what you care about, right? So if the vehicle is flying this way during entry, you want to yaw it maybe that way because that's your target. And so you yaw it that way, but then it also wants to roll. So you have to figure out how to stop that roll. And it's called trimming. You have to figure out how to trim out that roll. You have to figure out how to control that roll away, right? Because you yaw, and then it wants to roll some way. These are just graphs depicting that. So you have, at some non-zero side slip, you have yaw, like, okay, we're good with yaw, we're trimmed, and then you go and look at the roll, and you say, oh, you have some non-zero roll, and you have to be able to control that as well. But we designed this controllers to ideally be able to do alpha and beta. We weren't thinking about roll. So what does that mean? What does that mean for us? Yaw induces a roll moment that the vehicle needs to trim out. And this is just some additional plots saying, as a result of that roll moment that the vehicle needs to trim out, your side slip range is limited. So you don't want to yaw too much and then induce a roll that you can't control, because you didn't design to be able to control that roll. So you now kind of limit yourself in terms of side slip so you don't induce as much. And then when you limit yourself in terms of side slip, how good is your performance? How good is that guidance trajectory that's really depending? I mean, your guidance is thinking you have more to work with, but you don't. So that what does that mean for you? So basically, with the vehicle and the configuration we looked at, the side slip commands require constant roll reaction moments to trim. And if you do, that's for alpha, beta. Remember I said that there was bank angle command and there's alpha, beta. Bank angle requires roll moments only when the roll is changing. So what we showed with this trimmability characterization, how well we can trim, is that, okay, the control envelope for where the vehicle can trim will guide where guidance goes. What does your guidance trajectory look like? How far can you go, right? Because we're telling them now, okay, we can't go as far. The big finding is that alpha and beta have these coupled ranges due to that roll yaw coupling. And our window here is where we can operate successfully. And this window might not be sufficient for an optimum guidance trajectory. So Alpha beta is not possible for this vehicle in control configuration. So we can either look at bank, utilize the induced rule for bank. Remember I said we have bank and we have alpha beta. That vehicle was designed for bank with that asymmetry. Or we can redesign the control hardware to now say, okay, we have the ability to trim out any rule that's induced. So for this results, what I'm going to show you is we'll look at the latter. We're working on doing the former now, and maybe that'll be another presentation. I don't know if I have the bandwidth, but we're working on doing the latter, modify the control system to say, okay, now we're only going to do bank. The same thing, we're looking at the flap deflections, the moving masses, the jets on and off, and saying how well can we follow bank angle commands of rolling. So this roll is a problem, but how can we use it to our advantage for bank angle guidance trajectory tracking? So we did this yaw-to-bank architecture and the control design where we take our gains that drive the bank angle, convert them to basically a side slip. So we know that we have this coupled side slip roll interaction. Now we take that side slip command. There's papers on this, and I'll show the references. So you can take all the pictures you want. You can just go get an AIAA paper. So, so you take that bank, convert it to, you basically take the side slip command, and that side slip drives your bank angle utilizing that coupling. And this is a control architecture. If you're in controls, you always see feed like a block diagram like this. Controls peoples are major block diagram people. Question?
If you get into an uncontrollable pitch or roll, would that lead to a perpetual motion situation?
Yes.
Not much friction in space?
Yes. Yes, you can get it. And a lot of that characterization can be done way beforehand, right? There are things called stability derivatives, static stability derivatives, dynamic stability derivatives that should either be positive or negative. If it's negative, how negative is it? If it's positive, how positive is it? And if you're not stable, the linear quadratic regulator design that I showed does two things. It'll control and it will stabilize. Ideally, you should be able to control and stabilize, but you can check those things. Because if you're not stable and you get into a mode like that, you can start to roll to infinity and just, that's it. So what happens, like it's a thing, but you can check it before. You can check it before you fly. You can check, remove before flight. Yeah, but you can check these things beforehand. So that's what goes into that understanding the vehicle, that intuitive understanding of the vehicle, because it's garbage in, garbage out. If you don't understand the vehicle, if you don't understand what you're doing, you start with uninformed physics. You know, you can go through, these equations exist. You can always go through this process, but if you don't understand, it's garbage in, garbage out. And then you have a problem that you're having to explain to, to the world. So, so we did that, used that control design, and then, developed this control comparison metric to compare across all three designs. How well are these control designs in comparison to one another? And we looked at the bank angle acceleration. Yes?
Sorry, this is a misplaced question.
No.
The flaps, the only thing you're controlling is the extent or length to which they're deployed, or do you also adjust the angle?
The angle only, actually. So the length that they're deployed is fixed, and then it's the angle into the flow. So we don't control how far. That was one of the options.
Can you pivot also?
That will fix the roll problem. So that's what we're doing. That's what we're doing next, actually. So if you pivot, so the flaps, you can imagine the flaps like this, right? They're just going into the flow. So they generate a force. They're not able to really generate a force that is in this direction, right? And then so you can't roll or force them. I'm getting my 3D mixed up now. But if you were to pivot, then you're going to be able to generate more control authority in an additional axis. So instead of even like really pivoting, what about a twist? Like when you think about like these propellers, so that's what we're looking into next. Like that was the next step for this, and we're working. I had meetings today that we're talking twist angles and can angles and all of the options. We had time, we had money, so we went crazy. Yeah, but that's a great question. That's a great question. So we look at bank angle acceleration for how well we're doing. So this is a plot of during entry, your Mach number versus your dynamic pressure. So imagine the vehicle going through this. This is just like a sample guidance trajectory. Imagine a vehicle going through all of this. And we start our GNC activation somewhere on the top left. I don't know if you can see. Like at that point there, that says GNC activation. Then we go to we have this maximum dynamic pressure location, and then we don't go all the way to the bottom. Remember I said entry, we only care about the entry phase. And so we evaluate that metric that we've defined there at 2 different points of the flight envelope. Basically, how quickly can you accelerate using each of these systems? The bank angle acceleration, how fast can you go using those 3 control systems, and see how well you're doing. And so we saw that the RCS has a bank angle acceleration capability of about 11 degrees per second square, where the minimum that you have to have is 5 degrees per second square for a good trajectory. So RCS is good, but RCS better be good. It's heritage. It's what everyone's been doing, right? So it will be good. Then at max Q, we see that the flap control system is 11, like 115, it's 115. And the MMCS at max Q is 13.8. Remember, our bar is 5, right? So we have these flaps able to get us like so much more. At max Q, for the FCS, MCS is good, RCS is also good. But then at GNC activation, max Q is important because max Q is basically an artifact of your aerodynamic control surfaces depend on dynamic pressure. If there isn't enough pressure, if there is no dynamic pressure, your air control surfaces really can't do anything. So max Q is really important, but what happens at GNC activation in terms of these thresholds? GNC activation, your FCS is still fine, it's 11.5, but your MMCS is now 1.48. You are not able to achieve that bank angle acceleration for these vehicles for this configuration to meet even the limit of 5. So automatically, this has got to go. You throw this out. Yes? Oh, exactly. You know, we're comparing these 3. If this isn't going to work at GNC activation, it's not great enough. So these are just plots that show how well our RCS tracks. This is your bank angle. 2 plots, one's the truth, one is the command, and then we do the same for the FCS, beta, alpha, side slip, truth versus command, and they both track well. The MMCS we don't even show because we're not able to reach that threshold of bank angle acceleration. And the down selection we chose is to go with the flap control systems for these vehicles. It has exceptional control system capability, a notable available payload volume, and we can basically improve maneuverability in comparison to the RCS heritage vehicles, heritage designs. So in summary, we designed this control architecture that can handle either alpha, beta, or bank angle commands. It's a multi-input, multi-output linear quadratic regulator controller that allows for over-actuated vehicle control. So multi-input means there are many, could be 8 flaps, and the multi-output is like you're controlling 3 things, alpha, beta, bank, for example. This control design is adaptable to other vehicles and actuator configurations. The roll-yaw coupling renders alpha, beta infeasible for this vehicle, this control, this mission, and mechanical limits. And then the Yaw-to-bank, was an attractive solution for this. So the control capability estimate for Yaw-to-bank was the achievable bank acceleration with that side slip dependency. And the Yaw-to-bank basically leverages the roll-yaw coupling that is inherent with the vehicle to achieve increased maneuverability compared to the heritage RCS. FCS has the highest bank maneuverability, like I showed. It's 115 at max Q compared to the minimum that we need of 5. And then the control system recommendation from the controls guys is to go with the flap control system. So the key technical contributions of this work, it's one of the first that really, really closes a DV control system with hardware feasibility and guidance and controls performance. It's a really big deal. I'm really proud to be a part of this, effort. I mean, there have been other studies and some assumptions made we assume we can control roll, or we assume we can do this, or we assume that something will take care of it, but we kind of run the gamut and go through the start to finish what can be done. The impact is this enables further applications of inflatable or mechanical deployable entry vehicles for science mission and high mass missions to Mars and beyond. This tool set can be applied to any vehicle or control system, right? This work that's been done is not just for DVs. You can go through the process of doing this for any vehicle control system type. Do you have a question?
Are any rare metals used in the construction of these vehicles?
I'm unaware. I don't know. So I'm not a structures person. So the base, yeah. So your question is, are any rare metals used in the construction of spacecraft or deployable entry vehicles in general? Yes, he might have an answer.
You want something light, strong, and sometimes it's beryllium.
Yeah, beryllium, he said? Yeah, I don't know. So I'm not a structure, that's why I'm a controls girl. I'm not a structures person. I don't know what material will work or break, but you ask me a controls question and I hopefully have an answer for you. But I don't know, so that's an interesting question. There's a lot of work on the TPS, thermal protective system side at NASA Ames Research Center. So the big thing with these vehicles is basically withstanding the kind of thermal environments that these vehicles are subjected to. And we have arc jets that do a lot of testing. And the big one that we use here, I know, is HEAT, H-E-E-T, and even that is an acronym. No kidding. So yeah, so that's the big thing with us. We're really, really like kind of pushing the frontiers and boundaries with lightweight enough, but thermally like resistant material. Yes?
Fascinating. How would you be able to simulate that? I mean, in theory,
Yeah.
it's perfect.
Yeah.
How would you be able to simulate it at Ames?
Yeah, so the thermal protective stuff I talked about is actually like subjecting it to those thermal conditions that it will experience. And then there are a number of studies that will show you how doing some work in like simulation with some scaling factor depending on Reynolds number and things like that. But what we did here is a Python-based simulation for the controls team. Basically, see, I'm a MATLAB girl, so, and MATLAB is any MATLAB people in here? Yeah, I'm like, MATLAB is easy, MATLAB works, Simulink works, but this was a Python-based framework and simulation. So in simulation, you can do sims, but then future flight testing and future like suborbital flight tests are ideal next steps for this project if we get some additional funding. So if you have money, let me know. We'll take it. But it's a really, really cool project with some really, really exciting. And this, by the way, this is an early career project. Did I say that? All like the lead, the primary investigator, the principal investigator, and the team, like the core team, everyone leading all of the disciplines is an early career person. I started at Ames, less than 4 years ago? I got my PhD in 2015. These are early career people that, you give them money, you give them the opportunity, and we're ready to think outside the box. So if you give me money, we'll take it per any government regulations. Yes?
How does NASA decide whether something should be tackled in-house like an Ames, but they're better off just hiring somebody else to do it like Boeing?
I can't hear you. Can you repeat that question?
How does NASA decide whether...
What?
So for a project like this, how does NASA decide whether something needs to be tackled in-house, like at Ames, versus just hiring somebody else to do it, like Boeing?
Yeah, so this wasn't a project that NASA said, has to be tackled in a house. NASA actually gave the opportunity, was the Space Technology Mission Directorate that said, early career people, put your idea forward. So we weren't limited to this. There are requests for information, a number of calls and proposals that range from the most, very, very diverse things. So NASA doesn't really restrict anyone. We weren't required to do this. We just wanted to, we were interested. So NASA doesn't restrict their employees, their researchers, neither do they restrict outsiders as well. So there are many opportunities in many ways. You can do something on the outside, you can submit a proposal, you can answer, there are just a whole number of ways. And I share all of this like as much as I can on my Twitter and Instagram, like no kidding. I find something, I post it, I share it there, Wendy_Okolo. So if you have kids that are like, how do I get an internship at NASA? How do I do cool work at NASA? There are opportunities out there, and I share all of this. Like there's so many ways to get in and to do really, really exciting work. I'm gonna just kind of run through the summary of the key technical contributions, closing a novel control solution that makes asymmetric vehicle configurations controllable, and demonstrating the feasibility for vehicles not previously considered, non-traditional entry vehicles that can better serve mission needs versus traditional systems. So we identified this 100% non-propulsive entry control system. We have built this 6 DOF simulation test bed that will be completed this summer. The project ends in May, June of this year, and we are looking forward to redesigning the flap control architecture to enable alpha beta tracking and obtain follow-on funding for hardware prototyping, demonstrator, and a suborbital test flight in subsequent years if we're able to fund this and keep on doing the work. And here are the references to the papers, so you probably want to take a picture of this because there's like additional information of the different disciplines in here. I'm going to leave this up, and then yeah, please take your pictures. There's so many papers, especially AAA. We had a special session at AAA in January at AAA SciTech in Florida this January. And if the pictures are done, that brings me to the end of my presentation. What? Oh, okay. Okay. So yeah, he's saying if you have questions, to please go up to the mic. And thank you for your time. Yes. Okay.
You mentioned in your summary that there are some mission requirements that this extra maneuverability should help. Can you tell us what some of those are?
Sure. Yeah, like a sample lunar return, actually, which is what we were looking at. So, for example, if you imagine the Artemis program and the gateway that is supposed to be kind of semi-permanent. I mean, Danny can probably speak to this. Imagine being on that gateway and being able to launch something from gateway, but not requiring a heavy, like an actual capsule, but you want to bring something back to Earth. You want to bring a sample that you've gotten on the moon and now you're on the gateway and you want to be able to launch it from the gateway back to Earth. That's like the perfect one. So you can scale the size of this deployable entry vehicle. In fact, when we started out, we're 1+ meter. We've scaled it now. We're working with something that's like, I think 2.5. So there are different scalings and these architecture works. So a sample return is like the perfect one. A sample, not non-astronauts. They're not samples. Yes. Okay. Oh,
you know, when you were talking about the alpha and beta or the sigma, and you were actually in a two-dimensional model. And I was wondering if you had worked with a three-dimensional model to begin with, would that roll perhaps surfaced earlier? You could have done the model and then at some point set roll to 0 and perhaps come out with those values that, you know, the 5-degree angle that you were talking about. I'm just wondering about that. The mathematical model might have been broadened to 3 dimensions.
Right, we were actually working with a 6 degree of freedom, 6 DOF,
Okay.
XYZ, translation, XYZ, rotation.
Yeah, that's what I was thinking, XYZ.
Yeah, and so that's what we worked with, and that's actually what demonstrated this roll-yaw coupling. That's how we were able to find it, because we were working in multiple dimensions.
Okay.
But to kind of answer your question, you remember I talked about there's like static derivatives, stability derivatives that you can do beforehand to see. That can provide some kind of indication too. There's very, very low order, low fidelity analysis that can be done in terms of looking at your CL beta. So CL beta is like the coefficient of roll moment dependency on side slip. So as you vary your side slip, the roll moment coefficient changes. The roll moment has that dependency on CL beta. You can look at the magnitude of that CL beta to the magnitude of the CL that's generated by the flaps. So if you have a roll moment dependency on flap 1. You can call that like CL delta 1 or something. You can look at those magnitudes to see if the CL delta 1 or the roll moments generated by the flaps are comparable in magnitude to the CL that's generated from the base aeroshell's side slip. And if they're feasible, if they're close enough, you can kind of say, okay, well, we're doable, but that CL beta from the base aeroshell was pretty large. So and then that flap design, the flap design showed that the way the flaps were designed, we're not able to get a CL to counteract that CL beta. So we have to change the flaps, which leads to his point about twisting them.
Yes.
Yeah, exactly.
So when you were doing all those comparisons, and I saw a lot of deltas, so were you watching the deltas, and as soon as those deltas got to a certain limit, you were saying to yourself, okay.
Yes.
Were you also looking at perhaps intervals, like at this interval, these deltas are okay, at this interval, and maybe this one they're really out of whack?
Yes, so that's like a two-part question. The deltas, which are the flap, they have a saturation limit. which is plus 20 minus 45. You cannot go beyond or further than that, even if controls wants to. Aerothermal wouldn't let us. The second point about within a certain range we're good lends credence to that envelope that I showed for alpha beta. It's like, okay, within this range, you're good. But is that range good enough for guidance, trajectory, precision targeting? And then what if something happens and we get in an uncontrollable roll mode? Is that something we want to play with? So, we went the conservative angle and said, like, okay, let's go ahead and do bank. But we want to be able to expand that envelope and show that we can work outside of that envelope and rather expand the envelope and be able to generate some sort of roll moment control. Okay. Yeah, so we did both. Within some interval, you're good, and then we have saturation limits on the flaps.
Thank you.
Thank you.
So I have a question, but first I just want to say thank you. And I'm glad to hear that they're funding the young folks, because I know they're trying to do that also in the medical field, because there it takes years before they can run their own labs. So it's good to hear they're doing it. And it sounded like maybe it was your college education, some of the funding was the AIAA. So as someone who contributes to that, I'm glad to hear that too.
Yeah, it was primarily the Air Force Research Lab, actually. Through the Office of Scientific Research and through the AirFAR, the lab itself at Wright-Patterson, Ohio. I used to spend my summers there at Wright-Pat. Yeah.
Okay, my question though has to do with really where you fit in the bigger, your mission phase fits in the whole picture. And I'm just guessing, since I don't know the whole thing, that you're probably talking about some orbital vehicle that will then release this probes, not the right, anyway, the thing, the lander. And there's a phase where it comes off, and there's I know that you're studying a particular phase where you come up with the flaps work the best. Right. Obviously, it sounds like you hand it over to someone else to do the parachute part. But what I'm wondering about is when the vehicle first comes off the host vehicle, how would it be controlled when I'm assuming the atmosphere is too thin for flaps to work? I'm thinking about something like how the space shuttle, it used thrusters in space, and then it even had a period where it used both, and then when it landed, it only used the flap or the control surface.
So interesting question. That phase is spin stabilization, right when it comes right off the mothership, if you can kind of consider that. But it's typically RCS thrusters that it uses to stabilize.
It gets it spun up.
It gets spun, exactly, and so it needs to stabilize and then begin its entry. And that's not our focus, but it's actually a good. It's a very interesting thing to see if that is a regime that these non-propulsive control configurations can control. So maybe I could get an intern to. Study that.
If it's thin enough, they won't. I assume they won't have any effect.
Yeah, exactly. Exactly.
But and the thrusters to spin it up, are those coming down with it, or are they on a?
They come down with it, and they're also used for the propulsive RCS firing.
So there is a propulsion system.
Exactly. But they might work because remember I showed a GNC activation. We are at 11.5, where the minimum required but that was entry was like 5 degrees per second. So it could work. I'm not sure, but we haven't investigated that.
Okay.
Yeah. Okay. But spin stabilization uses RCS.
That's a good, simple way to do it.
Yeah. Thank you. Hi.
So how do you know where you are in space at the time?
How do I know where I am in space?
So if you're in space, how do you know where you are?
So like me or the spacecraft?
If an astronaut's in space, how do they know where they are?
An astronaut in space. I really, really hope we can keep track of our astronauts in space. So most times they're on the International Space Station, and we know exactly where that is, orbiting our Earth every 90 minutes. Other times, previously other times they're still attached to the space station in some regard and tethered and doing all these spacewalks, all these cool things that they're doing outside of the space station for like 7 hours on end. And then we've landed on the moon too, and we were watching them the whole time. So, but that's a good question. It comes into if that's what you're interested in when you're older, nav. You want to be in navigation. So guidance, navigation, and control. Navigation is where exactly are you? So remember that. GPS. Yeah, satellites, yeah. So that's how we know where you are. Spying on you. Okay.
The control software, I'm short, but not that short. Does the control software account for loss or jamming of one or more of the flaps, masses, or jets? And if so, what would be the maximum number of loss or the minimum required to maintain the control?
Yeah. So the multi-input, multi-output linear quadratic regulator design, you can actually set. So there's, I don't know how much we care about this. So you go through that process of, you have your nonlinear equations of motion, you linearize, you get through your linear system, and then you're trying to find this U equals K, X minus X desired, that K gain, and then you plug it back in. And I said your balance and objectives. Remember when I said your balance and objectives? Who remembers? That you can get here fast or a little slower. The way you do it in the control is through two matrices for the LQR. A Q matrix, which is telling you how you want your states to perform, and your R matrix, which is telling you how much of a control effort to use. So if you put a weighting number, like an entry in that R matrix that's really high, so let's say for you can imagine this R matrix as a diagonal matrix, right? So the first one is flap 1, flap 2, flap 3, all the way to flap 8. If I put a really, really high number here, it's gonna tell my control design that don't use this control surface, like barely use it, don't touch it. So through that, you can actually check if something happens, are we able to still fly and achieve the guidance trajectory? There will be some trade-off, of course, in terms of the performance, but you can do some of those studies beforehand and actually check, because you have those 8 flaps for, okay, maybe redundancy or increased control authority, but how well can you do it? So it depends on what it is you're actually trying to achieve in terms of the guidance trajectory, how fast are you trying to achieve it. But you can do some of those tests beforehand and basically say, no, we're good. We did some, and for the bank angle, we don't need all flaps. We don't need all 8 flaps for bank angle control. But remember, we designed those for alpha beta, and we did need them.
The shape of the vehicle, is that part of the algorithm or the implementation?
Yes.
And if so,
Yes.
Then potentially the loss of the flap could change the shape unexpectedly.
No, so we're not doing shape morphing, even though that is another part of controls, right? Shape morphing, moving masses, but the moving masses here is kind of a rigid form where you can kind of change the shape of the vehicle, but we're not doing that. We're assuming that it's this shell that we're not changing the shape for, but you can do some of that adaptive control work, and it's not a fixed LQR where your mass and inertia properties are changing. With some of those moving mass equations, you can. So I showed some equations, I took them out for brevity and ease for this presentation. But those equations can get really, really almost intractable, because now you have your masses moving, your masses accelerating. So you have mass positions of 1 through 8, positions, velocities, and accelerations. And this your states blow up from 8 to 31. So you can kind of do some of that, but we're working with a fixed mass and inertia here for what I said for the flap. So we're not doing shape morphing, no. But yeah, the big thing is you can check beforehand and see if you can put a weighting on any of those or multiple of those flaps and see how well you are able to control. Yeah, it's pretty cool, right? Who thinks this is cool? Yeah, everyone, it's pretty neat. Okay, well,
so I assume what you're doing right now is just a feasibility study. What does a development phase look like? What are the different major milestones? You have some hardware, you fly it, and a rough timeline for that. Assuming it carried forward. Right?
Yeah, so ideally to be able to carry it forward, this is what we want to do. We want to go to hardware prototyping, right? We already did a prototype of the flat designs, and we do a demonstration when people come to Ames. We can show that as well. But do the hardware prototyping, develop a test flight vehicle to explore this capability, and then feed forward technology to others that will need it, that will advance, the exploration of Mars and the other things that we want to do. So right now we're primarily heavily in the software design and development phase, and like you said, a feasibility study. But this is work that we want to see actually go forward, right? Even if it's not with us, we want to see that go forward.
When will be a first test reactor?
Yeah, so the funding ends June of this year, so that's it. Yeah, so unless you enable, that's, no, I'm kidding, but no, we're doing some work to see if we can get some follow-on funding to, you know, demonstrate this. There was a sub-orbital flight test for the Adept, like the baseline, pre-baseline vehicle a year or 2 years ago, and there's some results on that public information as well on AIAA. But yeah, but if we find something to hop on, we can go ahead and do. But this is just primarily software that has taken this much extensive effort, you know, from the team as a whole. But it'd be good to do some hardware prototyping and then actually see it fly. Yeah. Okay. Any other questions? Yes.
Which is worse from a controls perspective, direct entry at Mars or lunar sample return to Earth?
So, from a controls perspective, which is worse? That's an interesting question that I can't answer. Here's why, right? If we're doing FCS, if we're doing flap control systems and we care about our dynamic pressure, we care about the kind of control authority that we can get from our aerodynamic control surfaces. If we're doing RCS, and you just have thrusters and you can go ahead and, you know, work with that, you probably don't really care. But I do recall that the sample lunar return was chosen for like the stress loads, but it wasn't done in comparison to Mars. You know, it might have been done in comparison to like going there versus coming back. So I don't know. That's an interesting question. Like basically, I would first probably look at like characterizing the environment. I mean, it probably is harder to do Mars because how well has that environment been characterized, right, in comparison to our atmosphere, right? We know ours pretty well. We live here, right? So it'd probably be easier if you have all the right information, then you can design something that works, right? If you have the right information. But when you start dealing with uncertainties, particularly atmospheric uncertainties, aerodynamic uncertainties, then you have to start to design with a wider margin. And it's something to keep in mind. I think the uncertainties probably come into play there. So I don't know. Did that answer your question? It's like, yeah, if you know it all well, then you can make an informed decision. You can say this is easier than that. But if you don't know it well enough, then you don't know it well enough. Thank you. Okay. Any other questions? Going, gone. Thank you.